All right, so I've gone ahead and left everything written on the screen. I'm not going to do an example of this, but it's something I want you to file away in your back pocket. I know your back pocket is incredibly full of lots of things from Calc 1 and Calc 2 and Calc 3, but one more thing, hopefully it won't rip it. And here we go. If you have the surface integral of the curl of f, you should, as soon as you see this formula, you should be thinking, hey, I wonder if Stokes' theorem applies. Yet when you look at the context of what I've written, you immediately know it doesn't, because S is a closed surface. It doesn't have a boundary curve. And so you wonder what happens in that case. Well, let's use the divergence theorem. This surface integral of the curl of f becomes the triple integral of the divergence of the curl of f by the divergence theorem we studied back in 13.5. And we said, hey, anytime you take the divergence of the curl, you always get 0. And so the point is, the thing that I want you to file away is that the surface integral of the curl of f is just 0 whenever S is a closed surface, whenever it's the boundary of some simple solid region E. So I won't do an example of that, but do be aware of that. That might pop up in the final exam at some point. It's very possible. All right, well, let's do our last example together. I can't believe we're here, but here we are. So we want to find the surface integral, the flux of this guy, where S is the top half of the unit sphere. We're going to orient upward, and F is this interesting looking vector field. And so I wanted to go ahead and write this down just so that you'd have it, although looking now, my writing is kind of hard to read. Hopefully you can see it. When you parameterize a sphere, the first example that I did brought out the fact that the typical way of doing that with spherical coordinates kind of can get a little bit nasty. And you can imagine plugging that parameterization into this vector field and then dotting with that same r theta cross r phi, and it's going to be as bad or worse than the problem that we'd looked at before and said that we really didn't want to go down that road. And so I want to dream with you for a minute, and I want to imagine, hey, and before we dream, let's point out something. I've actually drawn this thinking ahead to what I'm going to do. It's really not quite right the way that I've done it, although it'd be hard to draw it any other way. I've got an S2 written there. This is not closed. This surface is not a closed surface. I want just the top half of the unit sphere. That's just this shell here. Let this go away. It's just the shell. It's not the bottom plate. That's open. And so the sort of dream is, man, I can't apply the divergence theorem because the divergence theorem only applies to closed surfaces. What if I could somehow close this up and recover the surface integral that I want? And as you know, dreams don't always come true. That's just reality, but sometimes they do come true. And in this case, what we really wish that we could close this up will work. And I wanted to show you how you can do that. So what I'm going to do is I'm going to think about S2 as the surface. That's the little plate here in the xy plane. It's the bottom of this sphere. And I'll think about just S, I guess, instead of S1, whatever, as the sides and the top of the unit sphere. And I want us to realize that if we add those up, if we take the surface integral of our vector field F over S plus the surface integral of our vector field F over not S1 but S2, then let me put a dot there. Okay, there we go. Now, together, this forms the surface integral of this entire closed surface, which I know is equal to the triple integral over the solid of the divergence of F. And the divergence of F, we should compute that. Let me scroll up where you can see. Let's change colors. I don't know, let's find something festive. So the divergence of F is, work it out with me. So it's going to be what? 2 minus 1 plus 5, which is just 6. So wow, that's really nice. So this is just and I forgot a dv here. This is just the triple integral over the top half of the unit sphere of 6 dv. We can use the same trick as before. We know that this, when I pop the 6 out, this is just 6 times the volume. This integral is equal to 6 times the volume of our solid, and in this case we have a formula for it. So this is exactly 6 times the volume of the unit sphere is 4 pi thirds, and we want half of that. And so you end up here with 4 pi. All right, so wow. Now, we've worked out this side. We want this piece. We know this piece. We know this piece. Sorry, we know this piece. We want this piece. And so if we can just figure out what this guy is, then we're going to be able to move it across and subtract or add, whatever the case may be, and we're going to have the surface integral that we want. So what the divergence theorem lets you do is you can close up your surface, and instead of trying to evaluate this nasty surface integral of this unit sphere, we can instead evaluate just this nice little disk in the xy plane, which is about as good as things can get, and then use the divergence theorem to get the surface integral that we want. So let's work it out together. So I'm going to work on S2 now. Make sure that I'm not, I was zoomed in a little bit too far. Let's zoom out a little bit. And here we go. So we're going to work now on S2. Just to be clear, this is going to be just the unit circle living in the xy plane, but we're thinking about it in 3 space. So I want to be careful here. This is the unit circle in the xy plane, but I am thinking about it here in 3 space. I need to parameterize it. And so, well, that hopefully is clear to you that we're just going to let x be x, and y can be y, and what does z need to be? Yeah, it's just 0. So this is going to be true for what? X squared plus y squared less than or equal to 1. And you know the formula. This is your g of x and y, so you know without working too hard that r partial x cross r partial y is negative g partial x is 0, negative g partial y of 0 is 0, and then a 1. Now, I want you to think about this. We have to be very careful here. We want to work with the divergence theorem, and the way that I did this, I didn't mention it when we worked through it, but I should have. The divergence theorem applies when your solid, when your surface that's a boundary of a solid has outward orientation. Now, that matches with the orientation that we wanted for S. We said S has upward orientation. That's good. But that means, since I'm going to use the divergence theorem, that means I need to orient this surface outward, i.e. downward. And so this is the wrong orientation. This points up. That's just pointing up in the z direction. So we're actually going to use, let's do this. We're going to use 0, 0, negative 1 pointing down. And so now I end up with the surface integral over the surface f2 of f dot ds2. And this becomes the double integral over my region D, which is the unit circle. And I'm going to take my function f. I should go get it. It's up here. And I'm going to, I want to actually copy it. And we'll just drag it along with us. So copy. And let's just put it right here, and then we can erase it in a minute. So I'm taking f, and I'm plugging in x is x, y is y, and z is 0. Everywhere you see a z becomes a 0. So this just is 2x plus y. Cosine of 0 is just 1, so I get a 1 minus y. And then this is 0, so I get an x squared plus a y squared. And I'm dotting with my normal vector 0, 0, negative 1, dA. Now we can erase our f, take that dot product, and wow, man, I like this. Everything cancels out, and I'm just left with a negative. Let's pop the negative out front, x squared plus y squared dA. This just smells very strongly of polar coordinates. We've got an x squared plus y squared. We've got a circle. Let's do it. So this is going to be negative integral. R goes from 0 to 1, theta goes from 0 to 2 pi, and what do we get? We get a r squared here, and then another r, so just r, we don't want highlighter everywhere, r cubed dr d theta. And so you can do this one in your head. The d theta is going to kick out a 2 pi, so we get a negative 2 pi times r to the 4th over 4, plug in 1 is just a quarter. And so we end up with negative pi halves. Okay, so now at this point, we've got everything we need to solve our problem. So let's go back, and I'm going to copy this, and I'm going to write it down below. So we got to here, and we said that the divergence of f was 4 pi. So the point is, we know that the surface integral over the surface that we want, S, the surface integral of f over S, plus the surface integral over the floor, S2, of ds2, this is 4 pi. But we know what this part is now. We got negative pi halves there. And so that means that the surface integral over S of f dot ds, this is the part of the top half of the unit sphere, it's the part that we were asked to compute. This is going to be what negative pi halves, move it over, becomes pi halves. So 4 pi plus pi halves, which is just 9 pi halves, and we've got it. All right. I wish I was there to give you a high five. You have made it to the end of Calculus 3 as far as the material goes. I probably will post another video. I'd like to post just a review, just a few comments reviewing Chapter 13. And I have uploaded a handout for you that has all the theorems that we've looked at in Chapter 13. It's already on Teams, so go ahead and grab that. And I might make a few comments just about how the ideas in Green's theorem, the fundamental theorem of line integrals, Stokes' theorem, and the divergence theorem, they all actually have a lot in common with the fundamental theorem of calculus. So I'll probably mention that in one more video. But as far as new material goes, you made it. Great job.